Okay, so today we're going to be talking about electrical resistance and Ohm's law. We've previously talked about voltage and current before, and resistance is going to be the third of those three concepts that really ties everything together. So, electrical resistance. So, resistance, if you see it in a formula, it'll have that uppercase R. The units are ohms, again named after someone, last name was Ohm, and you'll either see it written out as ohms or you'll see that symbol there, and that's actually the Greek letter omega. Okay, so if you see something that says 3 and then omega, it's 3 ohms. And that's the measure of the difficulty of passing an electric current through a substance or a device. And every material has a certain amount of resistance. And this is what determines if something is a conductor or an insulator. So a conductor would have very low resistance, allowing electricity to pass through it. An insulator would have very high resistance. Okay. So some material resistances. Now all of these are going to be for a 1 meter wire, that's about 3 feet. That's 1 millimeter thick. And if you remember to the other video when we talked about wire gauges, that would be about an 18 gauge wire. So first up we have carbon in the form of graphene. So this is carbon atoms arranged in a 1 atom thick sheet. And this is what actually has the lowest resistance of any material that we know of at room temperature. So this is about 3 milliohms, or 3 thousandths of an ohm. Next up we have silver, and this actually has the lowest resistance of any pure metal, and this is about a little bit over 5 milliohms. Next we have copper. So copper is a little bit more than silver, and if you're wondering, well, why do we use copper in our wires instead of silver, it really comes down to price. Copper is only a little bit more resistive, and it's a lot cheaper. And next we have mercury. So this is the only metal that's liquid at room temperature. And some old thermostats actually have mercury switches. So when the mercury heats up, it connects and closes a circuit. When it cools down, it shrinks and opens the circuit. So it is a conductor, but it's not nearly as good a conductor as silver or copper. Okay, next we have nichrome. So this is what you see in your toaster when you use it and it glows. So this is around 350 milliohms. Okay, so it needs to have some resistance in order to heat up the way it does. Next we have carbon in the form of graphite. So again, still carbon, but it's no longer arranged in a 1 atom sheet, it's just arranged in a random order. So this is what you see in your pencils. So this is around 796 milliohms, so we're getting close to 1 ohm. Next we have seawater, and you might see that 60,000 ohms and think, well, I thought seawater, was a good conductor. And it does conduct electricity, but it's not nearly as good as a lot of the metals or even graphite. And this is why if lightning strikes the ocean and you're a mile away, you're fine. If lightning strikes the ocean and you're within a few feet, you're going to be electrocuted. With drinking water, okay, it has around 6 million ohms or 6 mega ohms, and the reason there's that difference is because it doesn't have all that salt dissolved in it. Okay. Deionized water, otherwise known as distilled water. You'd find this in like a CVS, anywhere where you'd have to mix water with like a medicine, because it is 100% pure water. Every molecule that's not H2O has been taken out. So this is around 60 billion ohms or 60 gigaohms. Glass. So this is another one that's a very good insulator. Okay, so this actually has 10 quadrillion ohms or 10 petaohms. Okay, next up we have carbon in the form of diamond. So again, still carbon, but now all of the carbon atoms are arranged in a crystal lattice. Okay, and so this is about 100 quadrillion ohms. And then we have rubber. Okay, so this is around 1 quintillion ohms or 1 exaohm. This is why we use it to coat our wires when we're handling live voltage, well, we have rubber gloves. Okay, wood is another good insulator as long as it's dry. Okay, so this is about 10 exohms. Air itself is actually a good insulator. And when you think about it, it makes sense. If you walk past an outlet, a spark's not going to jump out of the outlet and hit you because it would have to go through that amount of air. And this is why lightning needs such a high voltage in order to make it all the way down to the ground through all that air. It's about 40 exohms. Lastly, we have Teflon. So this is 10,000 yada ohms, 10 octillion ohms. And this is what coats your skillets and pans to give that non-stick surface. And if you're wondering, that is the actual molecular formula for it. It's a lot of carbon and a lot of fluorine. And lastly, we have Ohm's law. So it says in an electrical circuit, the current passing through a resistor between 2 points is proportional to the voltage difference between the 2 points and is inversely proportional to the electrical resistance between the 2 points. So all of that probably didn't make that much sense. That's okay. All it really means is this formula down here. The voltage is going to be equal to the current times the resistance. Okay, so if I have a circuit and I increase the resistance, the current's going to go down. Hopefully that makes sense. And the reason that these triangles are here is because these three formulas are the same formula, just written in a different format. So if I cover up the V here, to find the V, it's I times R. I times R. If I want to find the current, so if I cover up the I get V over R, voltage over resistance. And if I want to find the resistance, okay, cover up the R, I get V over I. Resistance is voltage over current. So it's just a handy visual to help you use Ohm's law. And we'll be talking more about that when I do the demonstration with an actual circuit.